to this Good Friday seminar. So today we have one of our own PhD students. So it's a third year PhD student in the team of UXANA. And Karan will talk about the multiplicity of Wolf-Rayet stars. So please, Karan, I will give you immediately the floor.
Thanks a lot, Joris. So good afternoon, everyone. Thanks a lot for taking time on this Good Friday afternoon. My name is Karan, and I'm going to talk a bit about the work I've been doing in the past couple of years, specifically with galactic Wolf-Rayet stars and in the north. So a brief introduction to Wolf-Rayet stars. So massive stars, stars that have initial masses greater than 8 times the mass of our sun, end their lives through supernovae and leave behind remnants such as neutron stars and black holes. However, if your star is massive enough, so the threshold for massive enough depends on your favorite stellar evolutionary code and the metallicity. But so let's say more than 20 times the mass of the sun, then as it turns into a red supergiant, it manages to shed the outer hydrogen envelope. And then as a result of this, it goes towards the blue in the Hertzsprung-Russell diagram, and it appears as a Wolf-Rayet star. But what exactly is a Wolf-Rayet star? It is a spectroscopic class. So the initial definition of a Wolf-Rayet star was by two astronomers, Wolf and Rayet, and they basically observed the stars that had very broad and very strong emission lines in the spectrum. And they characterize this to the outflow from the stellar wind. So as you can see over here, this is a picture of WR124, and it has quite a large and strong stellar outflow, stellar wind outflow. And the stellar winds are very dense. They have densities the orders of magnitude larger than what you see for main sequence O stars. And because they are so dense, the optical depth of 2/3, which is where your spectrum is mostly formed, is far out in the wind. So we don't see the central photosphere, but what we actually see is the winds of these stars. So spectroscopically, so here I've plotted some stellar models from the code power. You see a lot of these broad and strong emission line features, and usually they're devoid of hydrogen. So they have a lot of helium features, and they have either nitrogen or carbon. The nitrogen in the spectrum is thought to come as a byproduct of hydrogen burning through the CNO cycle. And the carbon that you see is thought to be a byproduct of helium burning through the triple alpha process. So because of these elements that we observe, because of these features, we can put together a sort of an evolutionary scenario for these stars where main sequence O stars, if they are massive enough, might go through a transitionary phase where they have eruptive mass loss in a luminous blue variable phase, end up as Wolf-Rayet stars on the nitrogen sequence. So basically stars that show nitrogen in their spectrum, and then they evolve into stars that show carbon in their spectrum as helium burning products rise to the wind and that's what we see. And then they finally show some oxygen and end their lives as black holes. So this evolutionary scenario is called the modified Conte scenario, and I will be coming back to this later in the talk as well. Recently, however, we've been observing gravitational wave events, which are due to black hole binaries that merge within a Hubble time. So now then the question arose, okay, if black holes are formed usually from these massive O stars that go through the Wolf-Rayet phase, how do we get these black holes in binaries that are in periods that are short enough that they merge in a Hubble timescale? And to go back, we look at, because we're talking about black hole binaries, we're going to go back this evolutionary sequence and look at main sequence O stars. So main sequence O stars, most of them observationally have been found to be in interacting short period binaries. So a majority of them will interact in some way, shape or form over the course of their life. But the outcomes of this interaction are not very clear, not particularly clear. Also, when we look at the distribution of binaries for O stars, we see that most of them are at shorter periods of the order of days to months. So then the question is, okay, how does binary interaction affect this distribution? What happens to these stars? And because we have the modified Conti scenario, we have the evolutionary scenario, a way to answer these questions is to look at the distribution of Wolf-Rayet stars. And okay, if you have a lot of binary Wolf-Rayet stars, you look at their distributions, then you can see how evolution has actually affected these systems. So regarding Wolf-Rayet stars, there's a lot of discussion. And one of the main questions is their formation. How are they formed? Are they formed just because they are simply massive enough to strip their own envelope? Or are they formed predominantly through the stripping of their envelope through the presence of a binary companion? What is the binary fraction, which also leads into the previous discussion point. And in order to characterize these black hole systems, it would be useful to have the distribution of orbital periods and eccentricities for these Wolf-Rayet systems, since they are the immediate progenitors of black holes. And moreover, by observing stars in a binary system, you get a model independent constraint on the mass, which is very important because we have a constraint on the masses on the main sequence. And if we get the constraint on the masses at the Wolf-Rayet phase, we can make some link as to the mass loss rates because we know the evolutionary timescale. With all this in mind, we embarked on a homogeneous study of Wolf-Rayet stars in the galaxy that are observable with Hermes. The idea is to use spectroscopy and radial velocity, specifically radial velocities, to measure to see if we can find binaries, and not only that, to quantify the fraction of binaries in the Wolf-Rayet population. The reason we choose spectroscopy is because it's sensitive to periods of months to years, which is what the distribution of O stars showed. And finally, once we have an observed distribution of, once we have the observed binary fraction, we can then correct this for observational biases, because obviously we don't observe every Wolf-Rayet star in every particular orientation, orbital configuration, if it is in a binary. So that's the plan. So with that in mind, we looked at the galactic catalog of Wolf-Rayet stars, call it the GCWR. It was maintained by Paul Crowther from Sheffield. And from that, we had a magnitude cutoff and a declination cutoff because they need to be observable with Hermes. And the goal is that we get a signal to noise of 50 in the blue region. And that will allow us to get high quality and also high resolution spectra with which we can measure accurate radial velocities. So over here, you see the distribution by spectral type. And I broadly classified the nitrogen-rich Wolf-Rayet stars into early and late types. And that's just based on the strength of the line, the ratios of the line strengths. And you can see that in blue, some of the nitrogen-rich Wolf-Rayet stars have some hydrogen in them, which means that it's not really a discrete transitionary phase. There's sort of a spectrum, there's sort of a transition, smooth transition from O stars to Wolf-Rayet stars. Now, the spectra that we get from Hermes, so this is an example of what one of the spectra we get from Hermes, the 1D spectra. You can see a lot of telluric lines over here, and you can see that the shape is pretty well behaved, right? Now, the thing is, Wolf-Rayet stars, the spectra doesn't really have any continuum. So if I wanted to normalize the spectra, and for those, shout out to those who know the pain of normalizing spectra, I would have to fit a spline or some sort of a function through this. But because they don't really have a continuum, I'm going to have to choose continuum points that are below the spectrum itself. Now, this is problematic with respect to when I measure radial velocities, because if I put a point somewhere too high or too low, then the line profile can get skewed, and that can give me the assumption that something is moving when it's not actually moving. And this has been a big discussion even in the literature when working with Wolf-Rayet spectra. And so in order to tackle this, it is very important to, so we decided it was very important to tackle this. And so decided to correct the spectrum for instrumental effects and telluric lines. So this is what happens from the top panel to the bottom panel. So you see that we've removed the instrumental effects from the spectrum. And what we get as an output is supposed to be a reddened version of the stellar spectrum. So with continuum models, continuum SEDs from power, we find an anchor point in the red, and we're able to fit a reddened SED over here in the blue. And by dividing this, this gives us a normalized spectrum, and we're able to normalize all of our spectra in the same homogeneous method without thus reducing the chance of human error. So if there is a certain feature in the spectrum, it's going to be in all of the spectra, and that should not affect your radial velocities. But how do we measure radial velocities? So a brief recap. If you have a binary system and two stars are moving around a common center of mass, in our line of sight, the star will move forward and backward to some degree. And as the observable is in in their spectral features, the spectral features themselves will exhibit Doppler motion. So they will also move backward, back and forth. And depending on the amplitude of motion, we will see the amplitude of, we will see a bigger velocity if the motion is much bigger. And the idea is that if we randomly observe Wolf-Rayet stars and catch them at different points in their orbit, if they are in a binary, we should detect Doppler motion. And if we get Doppler motion, then we know that, okay, it might be in a binary. However, it's not so straightforward, specifically because Wolf-Rayet stars have very broad and very strong spectra. And I mentioned before that these spectra are formed in the wind, so they are very susceptible to variability that propagates to the wind. So any sort of clumping, any inhomogeneities, rotation, uh, and indeed these spectra are known to exhibit line profile variability of the order of on the time scale of days. And over here I just show an example for a star in my sample, and this is one of the one of the more extreme examples where the line profile varies up to a few percent in strength. And so with low resolution spectra, you wouldn't really see the change in the slope over here all too well. But with high resolution spectra, you actually catch it. And this is, while this is both a blessing, it is also a curse, because when measuring radial velocities, we need to keep this in mind, and we need to be aware of the fact that this can cause some sort of bias in our measurements. Okay, so the method that we use to measure radial velocities is called cross correlation. And cross correlation mathematically is just the convolution of a template with a data. So over here, I show a small GIF where I have a template in red, which I shift in velocity space or wavelength space, whichever you like to look at it. And I try to convolve it with the data. And the way I convolve it is not just a simple multiplication. I follow the methodology from Zucker 2003. And as a result, my cross correlation function, as a function of velocity, has a maximum amplitude of 1. And you can see that this template over here fits the data really well. So that's something you have to keep in mind, because the assumptions of the cross correlation method is that your template is an accurate representation of the data. Also, the peak was pretty smooth. Oh, sorry. The peak of the cross correlation function is pretty smooth and can be represented by a parabola, or traditionally you could fit it with a Gaussian, you could use a centroid, some sort of least squares fit to find the maximum. And the absolute value of the CCF is an indication of the goodness of fit. This is actually a very important feature, because when when we are measuring radial velocities for stars that have variable line profiles, then the absolute value of the CCF drops down. And that is a very important metric that we can use to quantify variability in the wind, variability in the spectrum. Right. So I'm going to take you through an example. So this is WR137. It's one of my favorite stars. It doesn't have a long telephone number, so that's a great thing. It is a known binary, so it's a WC7 with an O9 as a companion, and quite a long period, a period of 13 years, and slightly eccentric, right? So this is the normalized spectrum that we get from Hermes, and I'm going to show you, I'm highlighting here a few of the carbon-4 lines. So this spectrum shows features of carbon-4, carbon-3, and helium-2. But for now, I'm focusing on carbon-4. And I've also highlighted these lines based on their line strengths. So I have weak lines, strong lines, and moderate. I call them moderate lines, right? Lines of moderate strength. I'm going to try to use this spectrum itself as a template. So what that means is that I'm not using a spectral model. I'm not using something from Power, simply because spectral models for Wolf-Rayet stars do not accurately represent the line profile, of the spectrum itself, of the data. And as you remember, the important assumption is that your template should be an accurate representation of your data. And so I use the highest signal to noise observation for each star as a template. And then after measuring velocities, I create a co-added spectrum, which becomes an even higher signal to noise template. And then that's what I finally use to measure radial velocities. So these are some of the masks that I use, and I'm going to take you through whether this actually works, right? Because in the end, everybody likes to see a nice radial velocity plot. So for WR137, I plot over here the archival radial velocity curve from Lefebvre et al. 2005. And here you can see they trace out the orbit over 13 years, and this is as a function of phase. We measure, I plot overplot on this radial velocities measured with Hermes for the carbon-4 strong mask. And you can see over here, and these are shifted. These are shifted vertically in order to convert relative radial velocities to absolute radial velocities. And you can see that they are in good agreement. Now, the error bars over here are of the order of 1 to 2 kilometers per second. And you might ask me, oh, Karan, that those are quite small error bars, right? Didn't you say that Wolf-Rayet stars are affected by the winds? Like, how can you plot such small error bars? And indeed, you see over here, when you're looking at some points, that you don't have a smooth curve. You have some scatter in the points. And to answer your hypothetical question, I will say, yes, we thought about this. And for this long period binary, we chose a point that was far away from periastron, so where the O star is not interacting with the binary at all, with the Wolf-Rayet at all. And we observed this for about 2 weeks straight. And what we found is that depending on the mask you use, you get either values that are more or less the same, or values that are very erratic and they have a large scatter. So in black, the black points that you see are from a helium-2 line, which I use as a mask, a helium-2 weak lines. Now, helium-2 is a notorious line. So anybody who works with Wolf-Rayet spectra knows that helium-2 lines are very susceptible to any sort of wind variability, and they exhibit large-scale variability. And as a result, we are not surprised when we see this, when we see that they have a large scatter. Compared to which carbon-4 and the full spectrum, if I use the full spectrum as a mask, does not show much change, does not show much variability. So this shows that some lines are are affected by wind variability much more than others. And that's something that we want to keep in mind. So let's look at this a little more in detail. And then we see, okay, it's the same inset plot, but it's just bigger. So you have carbon-4 strong, the full spectrum, and helium-2 weak. Now, what if I wanted to look at within this short time scale, because I'm interested in how wind variability affects my measurements? What if I look in this short time scale at how the radial velocities change as a function of masks instead of a function of time? Because I know as a function of time, they should not change that much. So I can collapse the x-axis and instead swap it out with the masks. And what that results in is this. Excuse me. So yeah, on the x-axis over here, you have the different masks that we use to measure radial velocities. Some are carbon-4, some are helium-2, carbon-3. There's one oxygen-5 line, and then I can use the full spectrum. And this is within the same 2 weeks that I spoke about before. We measure something that's called the weighted standard deviation. So we call it sigma RV, in order to quantify how much scatter there is over this time period, over this time frame. And we see that for lines of carbon 4, so lines with a higher ionization, they show less scatter. The full spectrum shows less scatter, and weak lines show larger scatters compared compared to the others. So with this in mind, we can sort of wrap our heads around the fact that lines of a higher ionization state, or even the full spectrum, is not as susceptible to wind variability as we thought. However, so this is only for one star. If I wanted to to extend this same reasoning to each and every star in my sample is going to be a bit of a stretch. We do not have such short cadence data for all the stars in our sample. So this is the assumption that we make. And then we say, okay, for all the rest of the stars in our sample, we're going to focus on the full spectrum and then try to see what we find. And I show over here the same plot for WR113, which is also a known binary with a period of about a month. And over here, you see that we actually measure a large peak to peak amplitude in Doppler motion, even though our observations are randomly scattered in time. And you would also notice that there is some sort of a pattern where the red points are always more or less at the top, and then the green and the blue are somewhere in the middle, and then you have the yellow at the bottom, the yellow and the gray. So looking at this, I can say two things that, okay, so I can look at the sigma RV as a dispersion and I can say, okay, it's either bigger or smaller for some lines. And then I can also say that the peak to peak velocity is quite high. So these are more than the sigma RV, I'll be focusing on the peak to peak velocity. And I call this delta RV. So using this delta RV, we're going to try and talk about um, what fraction of our stars are in binaries. And these are the results from a paper that I published last year. So this plot is what is called a non-parametric threshold plot. And I'm going to take you step by step through it. So on the y-axis, you have the observed binary fraction, right? Simple. So that says just looking at the 12 carbon-rich stars in our sample, what fraction of this sample is considered a binary. And on the x-axis, I have this threshold. So say if I put my threshold at 40 kilometers per second, then WR113, which has a peak to peak amplitude or delta RV of 280 kilometers per second, can get classified as a binary, where the rest do not. Because I say anything that shows delta RV less than 40 kilometers per second is not a binary. You can do that exercise and start from large values of your threshold to small values of your threshold. If I put a threshold at, say, 15 kilometers per second, then I have 4 stars that get classified as a binary, whereas the rest do not. So you can play this exercise. And over here, I have written the names of the stars as they get classified as binaries. And in bold, there are names of there are binaries that are known in the literature. So in order to accommodate the known binaries in the literature, we decided upon a threshold of 10 kilometers per second, and that is a little low. It's a little on the lower side. However, one thing that you notice is that if these systems were in short period binaries, then they would show really high, really large amplitudes. And so far, we see only one of them. Granted, we do have a small sample, but this is something that we observe. and um, and yeah, so out of these stars, WR140 and WR137 are in really long period binaries. So they are in periods of 8 years and 13 years. So they are quite long. And these do not have detected periods yet. They have been classified as binaries either through the detection of absorption lines in the spectra, um, or because they are visual binaries. So that is something to keep in mind. So we have an observed binary fraction of 58%. Now the question is, how do you correct it for observational biases? And to do that, we perform Monte Carlo simulations. And the way we perform Monte Carlo simulations is that we assume a grid, construct a grid in log p space and M2 in secondary mass. So the period and secondary mass are are flat distributions in the values given over here, with separations of zero point 0.1 in log p and 1 solar mass in M2. We assume a flat distribution for eccentricity, an initial mass, a primary mass of 10 solar masses, and random inclinations, orientations of the orbit in space. Now, from the single stars in our sample, we fix the uncertainty on our radial velocity measurement to 1.6 kilometers per second. And with all these assumptions and with all this setup, for each point in our grid, we draw from these distributions, we draw parameters from these distributions and simulate 2500 time series, radial velocity time series for each object based on the number of epochs and sampling time that we have. So for each object, we would have at every grid point 2500 radial velocity time series. And with these time series, we look at what is the probability that the peak to peak amplitude would be larger than 10 kilometers per second. And that is the probability of us detecting the fact that it has such a peak to peak amplitude. And then for each object, we can construct these plots over here. So these are called detection probability plots. And I'm showing you the one for WR137. We've assumed the primary mass is 10 solar masses. And over here in a black X, I've indicated where the current solution for in period and mass ratio, where WR137 would lie. So from this plot, we notice two things. At low orbital periods, irrespective of where we are in the mass ratio, we would have a high detection probability. So if this system was in a short period binary, we would have detected it. And at very long periods, and at low mass ratios, we have a very low detection probability. And that is not surprising because our campaign has only been running for 2 or 3 years. So we cannot hope to sample orbital periods that are much larger than that. Oh, sorry about that. Yeah. So we then performed another Monte Carlo analysis with the same assumptions to try and reproduce some observational facts. We wanted 6 out of 11 objects in our sample to have peak-to-peak values between 10 and 30 kilometers per second. And the reason we exclude WR113 in this experiment is the fact that our prior distributions are way too simple to include just one object with a really large radial velocity amplitude. And so for the sake of the experiment, we excluded WR113 from this and just performed a few tests by changing the initial distribution for the period. We used a uniform distribution and a normal distribution. With varying widths and varying minimum maximum. And we also varied the intrinsic binary fraction. So what we say is that, okay, if our population had a binary fraction of say 50%, what was the probability, given the fact that we have drawn from all these distributions, what is the probability that 6 out of 11 objects show a peak to peak value between 10 and 30 kilometers per second? And what we found in our experiments by trying to play around with all of these knobs and parameters, what we found is that an intrinsic fraction of 0.9, so 90%, performs the best. However, we need to acknowledge that we have a small sample, and after correcting for it, we get an intrinsic fraction of between 0.72 and 1. So basically a binary fraction larger than 0.72. Now, if you look back to the modified Conti scenario, when I was talking about the evolution from main sequence O stars to Wolf-Rayet stars, we found a large fraction of them to be in interacting binaries. And our intrinsic fraction over here is also quite high, which means that it is possible that the binaries, the systems do not get disrupted. One more thing that we do realize is that for the O stars, we had a lot of binaries at short periods. But for the Wolf-Rayet stars, we barely detect, and especially for the carbon-rich Wolf-Rayet stars, we do not detect a lot of short period binaries. So by thinking about the evolutionary sequence, we can try to fit two pieces of the puzzle together and try to think about how these stars might have evolved. What would help is if I had stuff to tell you about the nitrogen-rich Wolf-Rayet stars, because they are the intermediate part, so to say. And these are very preliminary results. So this is for the nitrogen-rich, or the early nitrogen-rich sample. And what we see is already, so it's the same non-parametric threshold diagram. And what you see initially is that you have a lot more systems that are at short periods as compared to the carbon-rich Wolf-Rayet stars. And we've not decided upon where to put a threshold or what the binary fraction is. But in bold, you have the names of known binaries. WR157 was classified as a binary, but we've recently discovered it is actually a triple. And yes, so it does seem that the nitrogen-rich Wolf-Rayet stars seem to have a lot more short period systems as compared to the carbon-rich ones. And that is indeed something to think about. And so with that in mind, I'm going to leave you with my conclusions, and I'll take any questions. Thank you.
Thank you very much, Karen. Very nice talk. So I guess there will be some questions. If you have, please mention in the chat so I can call out your name. Please, Dominic.
Hi, Karan. Thanks for the talk. I'm going to put you on the spot. What's the shortest period Wolf-Rayet system that's known?
I think on the order of a day.
Okay.
1 day, I think.
Okay, that's interesting. And my second question, which is super selfish, is have you looked at WR7 in detail? Because as you and Toma know, it has caught my attention recently.
Yes, I have.
What can we say about the binarity of WR7? Because in your summary plots, you don't have it in bold.
No, it doesn't look like a binary, at least from, so I have looked at both the radial velocity plots themselves and the spectra to see if I see any Doppler motion, but I do not see any Doppler motion in the spectra.
Okay, that's interesting. Still left with a puzzle then.
Okay, thank you, Don. Pierre?
Yeah, thanks, Karen. Nice talk.
Thank you.
So I had a question, but actually there's one on this conclusion slide already. So you say on the last line, the WNE sample shows more short period systems. Could provide a hint. Which hint would that be? I mean, what would that tell? Possibly, how would you interpret that? Because it is, I mean, does this go along well with the Conti scenario, or or especially not?
I'm not 100% sure with respect to the Conti scenario as to what it says, but with respect to binary evolution, we do know. So the main question is what happens to all these short period main sequence O binaries? So what happens? Do they all merge? Does the system get disrupted, or what happens to it? And I think the fact that we see lesser and lesser short period systems as we get to more evolution, more evolved states, can say that maybe there is some physics in the common envelope that we are not quite certain about, or maybe they are all in triples, in which case that there would be even more things to think about. But I'm not 100% sure what we can say with respect to the evolution of these stars. But I think the main question to think about is, where do the short period systems go? So do they merge or do they get disrupted?
Yeah. And so that okay, so the short system could merge, and then then the others would have, the most evolved would have evolved then through a single star evolution or something, a continuum.
Yeah, probably, yes.
Yeah. But and then okay, maybe my original question was on slide 21. It's on the masks. So you show that you studied, basically, it's a bit of a detail, but you show that you studied many masks, which are dedicated to some lines, and one on the full spectrum. And you say that some lines are much more, like the helium lines are much more sensitive to the wind. Did you try something, not some specific lines, but the full spectrum, except maybe the helium lines, or except the weak lines?
I did, in my tests I did, thanks for the question. Like, it is actually an interesting thing that we could talk about it for a while. I did a lot of permutations and combinations when I was looking at what masks to use. So I would use all of the weak lines together, all of the strong lines together, the full spectrum minus the strong lines, minus the weak lines. And ultimately we converged on this. And the full spectrum minus the helium-2 does not make much of a difference as compared to the full spectrum. So to answer your particular question, the full spectrum does not show much of a difference as compared to the full spectrum minus the helium-2.
Yeah. Okay, thanks.
Yeah.
Great.
Okay, thank you. Then there is Matthias.
Yeah, thank Karan for the nice explanation. I was wondering, so you're doing a longer term monitoring of this of these systems. Is it actually possible, maybe along with archival data, to actually fit orbits for these binaries? I mean, certainly in the binaries, sort of right at the threshold, you might want to have. I mean, if you find a nice orbit fits, then you can definitely say this is a binary or not. So were you able to do that for any of these?
So we've not gotten to fitting orbits yet, but I suppose there are some plots that I can show for some of the known binaries where we've overplotted our data with archival data. So for example, this is WR140. So it's a very eccentric binary with a Wolf-Rayet star and an O star in an 8-year orbit. And so all of the Hermes data is in red, and that is all away from the periastron.
Yeah.
But it does, I think, in my opinion, it lines up very beautifully with what we have. But yeah, no, eventually the idea is that we will be fitting orbits for these systems, but that requires a lot of follow-up and a lot more data that we need to acquire.
Definitely.
Yeah.
Okay.
Thank you. Are there any other questions? Yes, Nicola.
Hey, Karan, nice presentation. So I also had a question that relates to this slide 21, where you showed different radial velocities that you measure for different masks. I didn't quite get why the variability would be higher for helium, or for example, is that because of the location where it's from the wind, or?
Yeah, so I think from what we understand about the winds is that helium-2 is, of course, a lower ionization species. And so it is formed much farther out in the wind where it's cooler. And in that extended, so as you go further out in the wind, you also have an extended part of the wind that gives you the spectrum. And if there are any inhomogeneities in the wind, they are much more likely to start out small in the inside and then grow as they go outward, as your simulations also show. And so if they grow as they go outwards, that's usually where helium-2 is thought to be formed. And so that's why the lines are affected by this.
So could we, or would it be possible to relate this back to then a sort of velocity dispersion as a function of radius, or is that maybe too far-fetched?
I'm not sure I understand. What do you mean velocity dispersion?
We have here the dispersion in the RV that you measure for different lines,
Ah, I see.
would this be related back to a velocity dispersion that you would see in simulations, for example?
Yes, but for that you would need to of course fit a particular model to this and understand exactly where these lines are formed. But yes, of course, it is definitely possible.
Right, thank you.
Okay, thanks. Any other questions? If not, then I would like to thank Karan again. Thank you very much.
Thanks a lot.
And I would like to remind all the people here so that